You can mute it right Okay, it is time to start, right? It's 1 o'clock. And let's go. Okay, so the homework assignment is due tonight. Let's finish all the questions that are left from chapter 21. So next week we have to finish chapter 22, which is a chapter connected to this one. Especially the two right-hand rules are going to be heavily used in the next chapter. The midterm is graded. The grades are on WebAssign. You can pick up your test whenever you want, well, after class or from my office later on. The grade distribution is there shown. So we have probably about, well, quite a few people that did very well, and there are people that didn't do so well. Since the material from the first midterm is going to be closely related to the next, to the material in the next midterm. If you didn't do so well on this midterm, you have to just learn this material. And if you do 80% or more on the next midterm, this midterm also becomes higher score if you didn't do that well. So you have incentive to really ace the next one, and after that, it will be much easier. You can pick up your test after class. Check again for grading mistakes and let me know if there is a grading mistake, but leave your questions after you review the test completely, rather than just talking to me immediately after you picked up. Okay, so that's any questions, any remarks related with this test? Yes. The next exam. So the next exam is again going to be after 3 chapters. So chapter 21, 22, and 23. And we're going to do the next midterm, hopefully, well before the midterm break. The material, again, is going to be very closely related with the material that we just covered. So just learn it. And the questions would be quite tricky, as you saw from the first midterm. The goal, again, is to get some proficiency with this material. Okay, any other questions there? No? Okay, so in that case, let me just summarize what we have so far. And practically, we talked about all sections from chapter 21. So we started with an expression for the force that acts on an electric charge that is in motion in magnetic field. And we said that it is a basic equation, the magnetic force acting on a charge with magnitude Q, moving with velocity V in magnetic field B is given with this expression. So you need sine of the angle theta, and the angle theta is the angle between the velocity vector and the magnetic field vector. So this is Lorenz's law. The direction of that force, the direction of the force that acts on this moving charge is given with the right-hand rule, the first one, the right-hand rule number 1. Well, after that, we know that electric currents are stream of moving electric charges. And therefore, a magnetic force also should act on a piece of wire with current if this piece of wire is also in external magnetic field. And the magnitude of the force acting on this piece of wire is proportional to the current that flows in this piece of wire, proportional to the length of this straight piece of wire, proportional to the magnetic field, and the sine of the angle again. Now the angle is between the current and the magnetic field, and the direction of the magnetic force again is given with the first right-hand rule. And finally, we talked about a rectangular wire with current in external magnetic field. And we saw that even though the net force acting on this rectangular frame with current, the net force is 0, but there is a torque that acts on this frame, and that torque makes that frame rotate around an axis that goes to the center of the frame. And the torque that is generated in this case happens to be a product of the current in the rectangular wire multiplied by the area of this rectangular wire multiplied by the magnetic field. And again, you have a sine of the angle, but this angle now is the angle between the perpendicular to the area and the magnetic field. So it is slightly different, but this expression basically describes how electric motors work. So the first part of chapter 21 is just dealing with magnetic forces that act either on currents or on moving electric charges in magnetic fields. So as a result of the magnetic force that acts on a point-like charge that is moving in magnetic field, moving in direction perpendicular to the magnetic field lines, we saw that this moving charge is going to curve in a circular trajectory.
What does sine represents again?
What does sine of the angle phi? So the angle phi here is the angle between the magnetic field vector and the normal to the area of the rectangular frame. So, well, the formula is important, but it is a result, this formula is a result of the previous formula. So using the previous formula, the formula about a straight piece of wire in magnetic field, you can determine the direction and the magnitude of the force acting on each of the four sides of the rectangular piece of wire with current, and the resulting force is going to be 0, but the torque acting on this rectangular frame is going to be whatever is here on the board. Okay, so the second part, yes. The second part of chapter 21 is a different story. It is related somehow in some weird way with the first part, but you can consider it as a different story. The second part of chapter 21 describes the magnitude and direction of the magnetic field generated by currents that flow in wires with different shapes. So the first formula is about a long straight piece of wire with current, like this. Current, let's say, flowing in upward direction in this diagram. And it can be shown that the magnetic field around this piece of wire with current is given with this expression. The magnetic field is proportional to the current in the wire and inversely proportional to the distance from the wire. In other words, the farther away you go from the wire, the weaker the magnetic field, as expected. The direction of that magnetic field is given with a different right-hand rule, the second right-hand rule. And the second right-hand rule says that the magnetic field lines are like circles around the wire with current. And this means that if the current is in upward direction here, the magnetic field lines are out of the board on this side of the wire and into the board on this side of the wire, into the board here. So again, depending upon what is the point of interest, the direction of the magnetic field created by this current is different. For example, the magnetic field here in front of the wire is in what direction? It's going to be this way, right, to your left. And the direction of the current of the magnetic field behind this wire is going to be this side, to your left. Okay. The second easy to write expression for the magnetic field created by a wire is the magnetic field created by a circular shape current. So current, let's say that is flowing this way along some circular or part of a circle shaped piece of wire. And unfortunately, the magnetic field at different spots around this circular loop with current is complicated expression. Only at the center of this circular loop, the magnetic field is easy to write, and it is equal in magnitude to mu naught times I divided by 2 times the radius of this circular loop with current. The second right-hand rule again gives you the direction of the magnetic field at the center and anywhere else for that matter. Again, the right-hand rule, the thumb in direction of the current, and the magnetic field lines are going to be like circles around your loop. In other words, at this particular point, the magnetic field is going to be into the board, while outside the loop, the magnetic field is going to be out of the board, out of the screen. And the final shape of wire with current, where you can write easily the magnetic field, is multiple loops like this next to each other, arranged in a form of a solenoid. Example here. Multiple loops right next to each other. If you put them in a spiral shape, they can be considered as if you have multiple circular loops right next to each other. And well, here's the solenoid, multiple loops. The magnetic field inside, everywhere inside this solenoid, everywhere but not too close to the ends of the solenoid, is going to be mu naught times the current times n, where n is the number of loops per unit length of the solenoid. In other words, n is equal to the number of loops divided by the entire length L, the entire length L of the solenoid. The direction of the magnetic field inside the solenoid is axial direction along the axis of this cylinder defined by the solenoid. And again, it is given by the right-hand rule. So is it this way or in opposite direction? Depends upon the direction of the current. In the homework assignment, you have several questions where you have to determine the direction of the magnetic field generated by a solenoid with current. And those are tricky questions. Pay attention to them. You are going to have similar questions on the next midterm. So they're really tricky. You have to see what is the direction of the magnetic field inside the solenoid. And if the magnetic field gets out of the solenoid from this side is going to work as if it is the north pole of the solenoid. And of course, the other side is going to come out to be south pole. And well, any remarks so far and questions? So you're tired from this entire week of classes that you're looking forward for yes.
So the area inside the solenoid will all be the same.
The volume inside the solenoid, the same magnetic field. This is the value of this, yes.
And the outside would be.
Outside the solenoid, you don't care. Outside of the solenoid, ideally, if the solenoid is infinitely long, very long, when you're outside, the magnetic field should be negligibly small. But again, we don't have infinitely long solenoids, so a calculation of the exact magnetic field for a finite length solenoid again is quite tricky, and you don't need to deal with it. Okay. Other remarks and questions? Okay. So what do you think? How was the first midterm? Easy? Not that easy?
Dr. Tatar,
Yeah.
she has a question.
Yeah.
Yes. So the charge leaving the solenoid is always north in direction.
So there are no electric charges inside the solenoid. The electric charges are flowing in the metal wire that makes the solenoid circumference, right? It is not the sides of, so this arrow represents the magnetic field. You cannot see it, but you can feel that magnetic field with a piece of iron or another permanent magnet. So basically, this solenoid with current in it acts as a permanent magnet, almost. Pretty close to a permanent magnet. And the magnetic field inside here, right here, inside that magnetic field is given with the expression that I have written. And you use solenoids everywhere where you want to easily turn on and off the magnetic field and therefore attract or not attract some piece of iron, right, in different relays and other devices. Okay, other remarks and questions? Well, so we have the magnetic field created by a current in a long piece of wire, magnetic field created by a current in a circular loop, magnetic field created by multiple circular loops forming a solenoid. What is the next shape that we should consider? well, the shapes don't end. We can keep going with different shapes until the cows come home, right? So we need a formula, a general expression that would describe the magnetic field created by any shape, current that is flowing along wire with any shape. And that formula is the third Maxwell equation called Ampere's law. And it is quite complicated, so you are never going to be asked to apply it, just because you have to do some vector calculus that is beyond what this course requires. But Ampere's law says the following thing. Let's say that you have some currents that are flowing along wires with arbitrary shape. So you have one current here, I1. You may have a current that is flowing in this weird shape, I2. To figure out the magnetic field created by multiple currents of this type, flowing in multiple shapes and directions, what you have to do is imagine a closed curve of arbitrary shape. It is imaginary curve, but it has to be closed, so it has to. And after that, take a small piece of this imaginary curve with length delta L, small, ideally infinitesimally small, and the magnetic field created by any currents in space at the place where this arbitrary length delta L is going to be some magnetic field which parallel to delta L component, be delta L. So take this delta L, take that magnetic field along the direction of delta L and multiply them. So you're going to have the parallel times delta L length. After that, take another small piece along your arbitrarily arbitrarily selected closed trajectory. Again, it is going to have some different, maybe, magnetic field in it, and so on until you go over the entire imaginary loop, imaginary curve. At the end, add all those products, and the result that you're going to get is going to be equal to mu naught times the total current that pierces the area defined by your closed loop. So this is quite tricky and complicated, but using the rules of vector calculus, you can calculate the magnetic field in any place in space. And this expression is called Ampere's law, and it is the third Maxwell equation, except that it needs a little bit of correction, a little bit of additional term, which we're not, in general, numerically, this additional term right here, numerically is, in most cases, much smaller than the rest of the terms in this equation. And it is not given in the textbook, and we're not going to deal with it. We're just going to forget about it. But a small correction term there is needed if you want electric charge to be conserved and Maxwell equations to be consistent with conservation of charge, conservation of energy, and everything that has to be conserved. So far, from the four Maxwell equations, we encountered three of the four Maxwell equations. The first Maxwell equation was Gauss's law, right? Gauss's law, which says that the electric flux that flows through arbitrary closed surface is equal to the total charge enclosed by that surface, divided by electric permittivity of vacuum. The second Maxwell equation, you can write it either as a formula or just state it as a sentence. The second Maxwell equation says magnetic monopoles do not exist. And well, as a formula, you can say that magnetic flux through arbitrarily shaped closed surface is equal to zero. If magnetic charges, if magnetic monopoles existed, you would have had an equation similar to Gauss's law. But since magnetic monopoles don't exist, on the right-hand side of this equation, you have zero. And the third Maxwell equation is Ampere's law, as stated here. So next week, we're going to deal with the fourth Maxwell equation, Faraday's law, next week. Any questions and remarks so far about this? Is pretty much everything that is in chapter 21. Any remarks, comments, questions? If not, let's look at problem number 12 from the homework assignment that is due tonight. Problem number 12. Okay. So people that are online can log into WebAssign and look at problem number 12. So in this problem, you are told that you have electrons that are moving fast with some kinetic energy that is given. They move horizontally from the west to east. So you have to imagine a map or something like a map. And you have a component of Earth's magnetic field that is pointing down, has certain value that they give us. And you want first to figure out the direction these electrons are going to be deflected. And second, you have to calculate the acceleration of those electrons as they are changing the direction of their speed. Well, what you have to use, of course, is the first equation on the board right here. So let's try to figure out the direction of the magnetic force that is acting on those moving electrons. The direction of the magnetic force. So they say that electrons are moving from west to east. So if you think about west here and east here, so maybe think about a horizontal map like this. Electrons, here is one electron that is moving this way, velocity vector this way. So electrons are negative particles. Their electric charge is negative. But the right-hand rule is for positive particles. So if you apply the right-hand rule, they say that, well, they say that the magnetic field component is in downward direction. So if you apply the right-hand rule, here is how to apply it. You have right hand right here, magnetic field in downward direction, a positive particle would feel a force into the board. But electrons are negatively charged particles, so the force that acts on them is going to be out of the board. And out of the board, in the notations in this problem, means that if this is west and east, this should be south. So this is the direction of the magnetic field force acting on those electrons. Well, if you have net force, you must have a net acceleration. Let's figure out the acceleration. Well, calculate the force, and the acceleration is going to come from there. Well, in order to calculate the force acting on an electron, you need the speed of that electron, the magnitude of velocity. And you can figure that out from the kinetic energy. So the kinetic energy of the electrons or any other particles is given with 1/2 mass of the electron multiplied by the speed squared. They give you this expression, right? For my version, that expression, call it K for kinetic energy. That expression for my version is, the number is 2.3 times 10 to the negative 15 joules for my version. And from here, you can say that the speed V is equal to 2 times the kinetic energy divided by the mass of the electron under the square root. You have to find the mass of the electron in kilograms from the cover of your textbook or from Google. And once you calculate that speed, you probably are going to get a substantial number, a number that would be of the order of some fraction of the speed of light in vacuum, which means that, strictly speaking, you have to use the rules of special relativity to get exactly what is going on here. But special relativity is not relevant for the case that we're considering. So just you have this expression for the speed of the electrons. From there, you can say that the magnetic force acting on an electron is going to be equal to the charge of the electron, which is one elementary charge in magnitude, no minus signs, times the speed that you calculated, times the magnetic field that is given to you, the component of the magnetic field that is given to you. And now look, the angle between the magnetic field vector and the velocity vector is 90 degrees, right here, 90-degree angle. Sine of 90 degrees is 1, so I don't need to enter any value for the sine of this angle. It is just a factor of 1. So this is the net force. In other words, the net force comes out to be, okay. Well, the battery is gone for a weekend, I guess, but we can continue without the battery. So you have charge E multiplied by square root of 2 times kinetic energy divided by the mass of the electron and multiplied by the magnetic field. But this is the force that acts on this electron. Newton's second law says total force, net force, is equal to mass times acceleration. And they're asking what is the acceleration. Solving for acceleration, you get that the acceleration of your electron is E times square root of 2k over m times v, all of this divided by the mass of the electron. Okay. Of course, TV tubes like this are not in use anymore, but this was the standard device for creating images just maybe 20 years ago. But still, moving charged particles, their acceleration is something that people still calculate when they want to figure out the momentum of those charged particles. In other words, this is, yes.
Can the masses not cancel out because of the term is underneath the square root?
So you cannot cancel out the mass, but you can rewrite this formula combining the mass in numerator and denominator like this. You can combine it and you're going to get, let's say, elementary electric charge square root of 2 times the kinetic energy times the magnetic field. And here you can get mass to power 3/2, let's say, if you want to write it this way. Or mass to power 3 under square root of whatever way you want. Whatever your calculator prefers, this is the notation that you can use. But unfortunately, you don't have a cancellation of the masses. So you have to find the mass of the electron from a table. Other questions? If not, let's go to problem number 14 from the homework assignment. Problem number 14. Okay, so this problem, I gave this problem, even though it is kind of trivial problem, I gave it because magnetic resonance devices are in use in most hospitals and in labs also. And here, in order magnetic resonance imaging to be practical, you need strong magnetic fields. Maybe not as strong as 8 Tesla, because 8 Tesla is huge. But a magnetic field of the order of 1 Tesla is reasonable magnetic field for magnetic resonance imaging. And they tell you that you have a solenoid creating a magnetic field. For my version, it is 8 Tesla. The current in the solenoid is 300 amps, very strong current. And you want to figure out how many turns this solenoid have, how many of those loops per unit length of the solenoid, per unit length this way. And look, it is a direct application of the formula that I had on the board and I erased, but we can write it again. So the formula says that magnetic field inside a solenoid is equal to magnetic permeability of air or vacuum multiplied by the current and multiplied by n, where n is the number of turns per unit length. N is exactly what they're asking we to find. They give us the magnetic field, they give us the current. Mu naught is a constant of nature, so you have to read it from a table. So solving for n, you get that the number of turns is equal to magnetic field divided by mu naught times the current. And it's going to give you some number of turns per meter of length of the solenoid. Of course, in modern magnetic resonance imaging devices, you use superconducting magnets, superconducting solenoids, which don't require so much energy, but they require cooling. They require sometimes, well, there are devices that are almost at nitrogen temperature, the temperature of boiling of nitrogen, but most superconducting magnets still need liquid helium for cooling. Yes.
What's mu naught equal to again? Sorry.
Mu naught is magnetic permeability of vacuum, universal constant of nature. Its numerical value you can read from a table, but it is also easy to remember because it is 4 pi times 10 to the negative 7th in SI units. Okay, other questions, remarks? So I guess that in this problem, just the constant mu naught is what is creating the confusion. So mu naught describes the magnetic properties of the medium around this current, around the solenoid, inside the solenoid. And the magnetic properties of vacuum and air are practically the same. So the value is the same. Other remarks? Okay, so the next question from the homework assignment is problem number 15. Problem number 15. So in this problem, you have to use another formula that I erased, a formula which gives you the magnetic field around long piece of wire, straight piece of wire with current in it. And that formula says that the magnetic field around current, long current with that goes in a straight wire is mu naught times the current divided by 2 pi r, where r is the distance from the wire. The farther away you go from the wire with current, the weaker the magnetic field created by this current becomes. In problem number 15, you have 4 of those straight pieces of wire, and you're asked to find the magnetic field at the center of the square. And well, using the right-hand rule, you can determine the direction of the magnetic field created by each of the sides of the square. So for example, this top side of the square, the current is this way. The magnetic field lines are like circles, right, around this current, which means that they enter on this side of the wire, they enter into the screen, into the board. In a similar way, into the board at that point, the current, the second current, the magnetic field created by the second current, the same direction, the magnetic field created by the third current, but the last current, the unknown current, creates magnetic field out of the board. So it has to be subtracted. So the total magnetic field at the center becomes. So let's introduce notations. So here is your square. Call this current I1, call this current I2, call this current I3, and of course the unknown current, they give it the direction in downward direction. So using those notations, the magnetic field at the center right here is going to be mu naught times the current I1 divided by 2 pi r, where r is half of the size of the side of the square. So for my version, R is 0.025 meters. So this is magnetic field into the board. The second current also creates magnetic field into the board, so you can add the magnetic field from the second current. You can add the magnetic field also from the third current because it also points into the board. But the magnetic field created by the unknown current is out of the board. So that magnetic field has to be subtracted in order to get the total. So you have negative mu naught times the unknown current divided again by 2 pi r. So this is your equation. The magnetic field, total magnetic field is given. Each of the currents is given. You have to solve for the unknown current. And well, you can rewrite this equation by factoring out the common factor. The common factor here is mu naught divided by 2 pi r. And in the brackets you have I1 plus I2 plus I3 minus the unknown current I. And from here, it is clear how to find the unknown current. So you just say that magnetic field times 2 pi r divided by mu naught is equal to the expression in the brackets. And now this means that the current I by itself is equal to I1 plus I2 plus I3 minus B times 2 pi r divided by mu naught. So this should be the answer. So notice that in this problem, figuring out the direction of each magnetic field at the point of interest was essential. Without those directions, you just cannot solve the problem. And you find the directions by using the right-hand rule, the second right-hand rule. Let's see, questions and remarks here. Yes.
So on this one, would we have to take that micro Tesla and convert it to a Tesla?
Oh, yes, yes. So this micro Tesla is 10 to the negative 6. So you have to use that value for the total magnetic field. 10 to the negative 6 is micro Tesla, yes. And look, the magnetic field created by the currents that are flowing here in this room, usually the current in this wire or the wires in the wall, are of the same order, right? They're not very strong because the currents are not strong. Of course, those magnetic fields change their direction 60 times per second because the current that is flowing in the grid is AC current changing its direction multiple times per second. Okay, other questions and remarks? So we still have 1 more minute, and let's, you can pick up your test. The tests are alphabetically ordered according to last name. And again, look at the test. If you have questions, first check the test very well and find all the questions that you may have. Also, make sure that you check for grading mistakes. So alphabetized last name, A, B, and so on.